Okay, so what I want to establish is where the heck did Ben get all those coefficients from that he seemed to be guessing randomly, that there's no way that you can guess those numbers so randomly and have it come out so nicely and have there be a pattern to them and the whole nine. So one of the things that we didn't talk about is where series are centered, okay, and we talked about the center being the kiss, okay, where they touch. It's that perfect point where they definitely for sure agree, but we didn't talk about what we're going to see when or how the terms of the series will look and how that'll indicate where the center is. And one of the things that everything that we've looked at so far has been centered at 0, but what I want to establish as what the center is. Okay, the center is going to be the number you can plug into your series that will make every term but the first term go away, okay, meaning subtract to 0 or just become 0. That's what I mean by go away. So if I look at this series up here, which is a general form of a series, I have a c sub 0 plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a cubed. Those c's, the c sub 0, c sub 1, c sub 2, c sub 3, c sub 4, and so on. I have a plus dot 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 to say and so on. That's why I have an f of x equals instead of an approximate. Those are just coefficients, okay? And that's just going to be the pattern of any of our Taylor polynomials. I have a number plus a number times x to the first power plus a number times x to the second power plus a number times x to the third power and so on. And the reason that I have these x minus a's is that allows my center of my series to be anywhere. All the series that we've looked at have been centered at 0, okay? But this series is going to be centered where whatever I'm going to plug in for x is going to make all the terms but the first one go away, and that would be, I'd have to plug in a for x, and then each of these little things here, all of these x minus a's to the first power, second power, third power, they would all become 0, okay? So that's how I see what's in, so it's what's being subtracted by my x before it's raised to a power, or it's the number that I'm plugging in that's going to make all the terms but the first go away, but all those little terms are going to become 0 if I plug in a, so this series is centered at a. Okay, so again, the reason the center is important is that it's where that kiss is happening, and the hug has to branch out from there. Okay, so this series is centered at x equals a. It's a general form of a Taylor series, and again, if I wanted a Taylor polynomial instead of a Taylor series, I would just truncate it. I'd chop it off. I'd chop off that plus dot dot dot. So if I want to figure out what c sub 0 is, okay, look at this function and figure out how I'm going to figure out what c sub 0 is. I essentially want to isolate the c sub 0. What will I do? Okay, pause, think about it, come back to me. Okay, and in order to find the c sub 0, I want all the other terms to go away, and that's where I'm going to utilize that center. So if I plug in a into f of x, I'll have f of a will be c sub 0 plus c sub 1 times 0 plus c sub 2 times 0 squared plus c sub 3 times 0 cubed and so on, which will just give me c sub 0 plus 0 plus 0 plus 0, or just c sub 0. So therefore, c sub 0 is just f of a. Okay. All right, and again, what we're trying to do here is just to figure out how to determine those coefficients and where did Ben come up with those coefficients from. So let's talk about how to find c sub 1. Okay, and I want you guys to think about, to find c sub 0 and get the only term there to be c sub 0, I was plugging in a for x, and that got rid of all the terms but c sub 0. Okay, if I want to find c sub 1, I want to isolate c sub 1 and not have it c sub 1 times x minus a, not have it plus c sub 0 plus c sub 2 times blah blah blah, all the other crap. I just want a c sub 1. I need to somehow get rid of c sub 0, which is a constant. I need to also get rid of c sub 1 times x minus a. I need to get rid of that. And then all the other terms, if I plug in a, I'll get 0 for. So how am I going to get rid of a constant and get rid of an x to the first power and make it no x's at all? Well, the answer set is by taking a derivative. So what would the derivative look like? Pause it, take the derivative of f, and come back to me. Okay, so if I take the derivative of c sub 0, it's a derivative constant would be 0, and then the derivative of c sub 1 times x minus a, I would hold the coefficient of c sub 1, and then the derivative of x minus a to the first power would just be, you can either just take the derivative of a linear function, you get 1, or you could drop down an exponent or reduce it by 1, you get a 1 times x minus a to the 0, which is just 1. But so I got c1, and then for the derivative of c2 times x minus a squared, I'm going to hold the c2, drop down the exponent, so that gives me 2c2, times reduce the exponent by 1. I'll have x minus a to the first power. The inside stays the same times literally inside, which is b1, plus hold the c sub 3, drop down the exponent, reduce it by 1. Inside stays the same times literally inside. I get 3 sub 3 3c sub 3 times x minus a squared. And then plus, I'm going to, on my next term, I drop down the 4c4 times x minus a cubed, and so on. Okay, now if I want to isolate c sub 1, what am I going to do? I'm going to plug in a into my derivative. And what would I have? Okay, so f prime of a would be c1 plus 0 plus 0 plus 0 plus 0 plus 0. So f prime of a is c1, so c sub 1 is just f prime of a. Okay, and sorry for the funny looking prime marks, but my program is being a little wonky for me. Alright, if I want to now isolate the c sub 2 to figure out what that coefficient's going to be, I need to, I'm hoping you guessed it, but if you need to, pause and think about it. Go ahead and pause and come back. But I'm going to need to take a second derivative. So think about what that second derivative would look like. Take the second derivative, pause, and come back. Okay, my second derivative, the derivative of c sub 1 is just a coefficient now, so when I take the derivative constant, so when I take the derivative of it, I'm going to get 0. And then when I take the derivative of 2c2 times x minus a to the first, I hold the coefficient 2c2, and the derivative of x minus a is 1, plus I had a 3c3. I'm going to hold that coefficient, and I'm not going to simplify anything because you guys know how lazy I am without my calculator, and I don't want to get big numbers. So I'm just going to leave a string of products. I'm not going to simplify them. So, and just FYI, my big capital C's and my lowercase c's, they're all the same. It's just the program is being a little fickle with me about whether it's going to draw me a capital C or a little lowercase c. So just all the C's are big C1 is the same as little c1. Big C2 is the same as little c2. Okay, so so I'm going to hold the 3c3, and then I'm going to drop down on x minus a squared. I'm going to drop down that exponent and reduce it by 1. So I have 3 times 2 times c3 times x minus a down to the first power. And then on my 4c4, I'm going to drop down the exponent. I'm going to hold the 4c4, drop down the exponent, reduce it by 1. So I end up with 4 times 3 times c4 times x minus a squared, and so on. How am I going to isolate c sub 2? Well, I'm going to plug in a again, but now into the second derivative. So that'll look like this. Okay, if I plug in a into the second derivative now, I'm not going to end up just with c2. I'm going to end up with 2c2 plus 0 plus 0 plus 0, which is just 2c2. So if I want to solve for c sub 2, I would have to think about it, I'd have to do f double prime of a divide by 2. Okay, so c sub 2 is going to be f double prime of a divided by 2. Alright, go ahead, to find c sub 3, I'm going to have to take a third derivative. Go ahead and find me the third derivative. And that should look like this. Okay, the derivative of 2c2, the derivative constant is 0. The derivative of 3 times 2 times c3 times x minus a to the first, I'm going to hold the coefficient, and the derivative of x minus a to the first is just 1. And then my 4 times 3 c4, I hold that coefficient, I drop down my exponent, which is where I get my 4 times 3 times 2 times c4 times x minus a to the first, and so on. And now this time I'm going to, well, again, plug in a into my third derivative. And if I plug in a to my third derivative, I will have, okay, so my third derivative will be 3 times 2 times c3, and all the other terms will go out to 0. Okay, so if I want to find c sub 3, I'm going to divide by 3 times 2. And again, I don't want numbers to get big, so I'm just going to leave things like that. Sorry, everything's being fickle today, so I can't shrink that anymore, so I know it's all kind of on top of each other. So now, if you guys wanted c sub 4, think about what c sub 4 would look like. Well, first of all, let's think about what the fourth derivative would give me, evaluated at a. So think about what the fourth derivative evaluated at a would look like, and then figure out what c sub 4 would look like. Okay, so hopefully you pause before you come back to me, but okay, so the fourth derivative evaluated at a would be 4 times 3 times 2 times c4, and that would make c sub 4 would be the fourth derivative evaluated at a over 4 times 3 times 2. And I'm hoping at this point you're getting the impression, or the idea of why I was not simplifying any of those things before. I have an f prime of a divided by nothing, which I can also say is divided by 1. My f double prime of a divided by 2, which I could also say is 2 times 1. My f triple prime of a divided by 3 times 2, I could say 3 times 2 times 1. And my fourth derivative evaluated at a divided by 4 times 3 times 2 times 1. Hopefully you're recognizing some factorials. So I want you guys to go ahead and take the nth derivative, or write out what the nth derivative would look like. Pause and come back to me. Okay, my nth my nth derivative would be n factorial times c sub n plus a bunch of other terms that have a bunch of factorial-like coefficients with a bunch of x minus a's in them. So if I go ahead and found the nth derivative evaluated at a, I would have, okay, so my nth derivative evaluated at a would be n factorial times c sub n, right? All the other terms would go out to 0, and then c sub n would be, pause and write it out and come back to me. Okay, so c sub n would be the nth derivative evaluated at a over n factorial. Okay, so I know this all seemed like a lot of work and a lot of time has gone by, but we've just come up with a systematic approach for finding those coefficients. Okay, so what I'm going to do in the next slide is I'm going to replace all of these coefficients, okay, our c sub 0, our c sub 1, our c sub 2, our c sub 3, our c sub 4, and so on, with what we figured out they would be over here. Okay, so that's what I'm going to do in our next slide. Okay, so actually this one too. Okay, so that's what you should expect to see. Actually, maybe you should do that first, pause, and then come back to me. Okay, so replacing all those coefficients, you'll get more of an idea of where Ben got those coefficients from. Okay, so my initial constant in the front is going to actually be f of a, plus the coefficient on my x minus a to the first power will be f prime of a over 1 factorial, plus f double prime of a over 2 factorial times x minus a squared, plus f triple prime of a over 3 factorial times x minus a cubed, plus and so on, the nth derivative evaluated at a over n factorial times x minus a to the n. Okay, so what we have here is our general form. This is a very, very important formula for you to memorize. You're going to be using it over and over and over and over again. Okay, so just as far as the general form of this series goes, I'm going to have the sum from n equals 0 to infinity of the nth derivative evaluated at a over n factorial times x minus a to the n. And again, I really can't stress enough how important that is. Okay, the whole process and this end result. Okay, now because I have an infinite series, right, I'm summing from n equals 0 to infinity, I have f of x equals, right, if I just had a finite number of terms in here, I'd have to have an f of x as approximately. Okay, but this is called the Taylor series for f centered at a. Okay, and if the series is centered at x equals 0, then think about what would happen if you plugged in 0 in place of every a up top and try to write out what that would look like for me, please. Okay, and if I'm centered at 0, it's a Maclaurin series instead of a Taylor series. All right, like I said, it's just a special, it's what was said before, a Maclaurin series is a special type of Taylor series centered at 0. So replace all your a's with zeros and write out what that would look like. Okay, so I put it down here because I didn't really have enough space. So I have f of 0 plus f prime of 0 over 1 factorial times x minus 0 to the first versus x to the first, plus f prime of 0 over 2 factorial x squared, and so on, which would look like the sum from n equals 0 to infinity of the nth derivative evaluated at 0 over n factorial times x to the n. Okay, and there's our derivation for both our Taylor series and our Maclaurin series. Okay. I am almost out of time, so we will pick up with the examples in the part 2 video for this. And I promise you everything that we just did will make more sense once we apply it.